A set is any collection of objects, all of which are known as the elements of the set. The statement, capital A equal to, brace open, 1, 2, 3, brace closed, is read. A is the set of elements 1, 2, and 3. In geometry, geometric figures such as lines and angles are actually sets of points. Where capital A equals the set of elements 1, 2, and 3, and capital B equals the set of counting numbers, A is a subset of B because each element in A is also in B. In symbols, A is a subset of B. Definition: a statement is a set of words and symbols that collectively make a claim that can be classified as true or false. Classify each of the following as a true statement, a false statement, or neither. Number 1. 4 plus 3 equals 7. True statement. Number 2. An angle has two sides. See figure 1.1. True statement. Number 3. Robert E. Lee played shortstop for the Yankees. False statement. Number 4. 7 is less than 3. This is read, 7 is less than 3. False statement. Number 5. Look out! Neither. This is not a statement. Some statements contain one or more variables. A variable is a letter that represents an unknown number. The claim x plus 5 equals 6 is called an open sentence or open statement because it can be classified as true or false depending on the replacement value of x. For instance, x plus 5 equals 6 is true if x equals 1. For x not equal to 1, x plus 5 equals 6 is false. Some statements containing variables are classified as true because they are true for all replacements. Consider the commutative property of addition, usually stated in the form a plus b equals b plus a. In words, this property states that the same result is obtained when two numbers are added in either order. For instance, when a equals 4 and b equals 7, it follows that 4 plus 7 is equal to 7 plus 4. The negation of a given statement, capital P, makes a claim opposite that of the original statement. If the given statement is true, its negation is false, and vice versa. If capital P is a statement, we use not capital P, which is read not capital P, to indicate its negation. A compound statement is formed by combining other statements used as building blocks. In such cases, we may use letters such as capital P and capital Q to represent simple statements. For example, the letter capital P may refer to the statement 4 plus 3 equals 7, and the letter capital Q to the statement Babe Ruth was a U.S. president. The statement 4 plus 3 equals 7 and Babe Ruth was a U.S. president has the form capital P and capital Q and is known as the conjunction of P and Q. The statement 4 plus 3 equals 7 or Babe Ruth was a U.S. president has the form capital P or capital Q and is known as the disjunction of P and Q. A conjunction is true only when capital P and capital Q are both true. A disjunction is false only when capital P and capital Q are both false. The statement, if capital P, then capital Q, known as a conditional statement or implication, is classified as true or false as a whole. A statement of this form can be written in equivalent forms. For instance, the conditional statement, if an angle is a right angle, then it measures 90 degrees, is equivalent to the statement, all right angles measure 90 degrees. In the conditional statement, if P, then Q, P is the hypothesis and Q is the conclusion. Hypothesis: two sides of a triangle are equal in length. Conclusion: two angles of the triangle are equal in measure. For the true statement, if P, then Q, the hypothetical situation described in P implies the conclusion described in Q. This type of statement is often used in reasoning, so we turn our attention to this matter. Success in the study of geometry requires vocabulary development, attention to detail and order, supporting claims, and thinking. Reasoning is a process based on experience and principles that allow one to arrive at a conclusion. The following types of reasoning are used to develop mathematical principles. Number 1, intuition, an inspiration leading to the statement of a theory. Number 2, induction, an organized effort to test and validate the theory. Number 3, deduction, a formal argument that proves the tested theory. Intuition. We are often inspired to think and say, "It occurs to me that." With intuition, a sudden insight allows one to make a statement without applying any formal reasoning. When intuition is used, we sometimes err by jumping to conclusions. In a cartoon, the character having the bright idea, using intuition, is shown with a light bulb next to her or his head. Figure 1.3 is called a regular pentagon because its 5 sides have equal lengths and its angles have equal measures. What do you suspect is true of the lengths of the dashed parts of lines from B to E and from B to D? Intuition suggests that the lengths of the dashed parts of lines, known as diagonals of the pentagon, are the same. The role intuition plays in formulating mathematical thoughts is truly significant, but to have an idea is not enough. Testing a theory may lead to a revision of the theory or even to its total rejection. If a theory stands up to testing, it moves one step closer to becoming mathematical law. Induction. We often use specific observations and experiments to draw a general conclusion. This type of reasoning is called induction. As you would expect, the observation/experimentation process is common in laboratory and clinical settings. Chemists, physicists, doctors, psychologists, weather forecasters, and many others use collected data as a basis for drawing conclusions, and so will we. In a geometry class, you've been asked to measure the 3 interior angles of each triangle in Figure 1.4. You discover that triangles 1, 2, and 4 have 2 angles, as marked, that have equal measures. What may you conclude? Conclusion: the triangles that have 2 sides of equal length also have 2 angles of equal measure. Deduction. Deduction is the type of reasoning in which the knowledge and acceptance of selected assumptions guarantee the truth of a particular conclusion. In Example 8, we will illustrate the form of deductive reasoning used most frequently in the development of geometry. In this form, known as a valid argument, at least 2 statements are treated as facts. These assumptions are called the premises of the argument. On the basis of the premises, a particular conclusion must follow. This form of deduction is called the law of detachment. If you accept the following statements 1 and 2 as true, what must you conclude? Number 1. If a student plays on the Rockville High School boys varsity basketball team, then he is a talented athlete. Number 2. Todd plays on the Rockville High School boys varsity basketball team. Conclusion: Todd is a talented athlete. To more easily recognize this pattern for deductive reasoning, we use letters to represent statements in the following generalization. Law of detachment. Let P and Q represent simple statements and assume that statements 1 and 2 are true. Then a valid argument having conclusion C has the form: Number 1, if P, then Q. Number 2, P. Premises. C, therefore Q. Conclusion. Note, the symbol 3 dots in a triangle means therefore. In the preceding form, the statement if P then Q is often read P implies Q. That is, when P is known to be true, Q must follow. We will use deductive reasoning throughout our work in geometry. For example, suppose that you know these 2 facts. Number 1, if an angle is a right angle, then it measures 90 degrees. Number 2, angle A is a right angle. Then you may conclude, C, angle A measures 90 degrees. Sets of objects are often represented by geometric figures known as Venn diagrams. Their creator, John Venn, was an Englishman who lived from 1834 to 1923. In a Venn diagram, each set is represented by a closed, bounded, figure such as a circle or rectangle. If statements P and Q of the conditional statement, if P then Q, are represented by sets of objects P and Q, respectively, then the law of detachment can be justified by a geometric argument. When a Venn diagram is used to represent the statement if P then Q, it is absolutely necessary that circle P lies in circle Q. That is, P is a subset of Q. See Figure 1.5. Use Venn diagrams to verify if you accept the following statements 1 and 2 as true. What must you conclude? Number 1. If a student plays on the Rockville High School boys varsity basketball team, then he is a talented athlete. Number 2. Todd plays on the Rockville High School boys varsity basketball team. Let B equal the students on the Rockville High School varsity boys basketball team. Let A equal people who are talented athletes. To represent the statement if a basketball player, B, then a talented athlete, A, we show B within A. In Figure 1.6, we use point T to represent Todd, a person on the basketball team, T in B. With point T also in circle A, we conclude that Todd is a talented athlete. The statement if P then Q is sometimes expressed in the form all P are Q. For instance, the conditional statement of examples 8 and 11 can be written all Rockville High School players are talented athletes. The compound statements known as the conjunction and the disjunction can also be related to the intersection and union of sets, relationships that can be illustrated by the use of Venn diagrams. For the Venn diagram, we assume that the sets P and Q may have elements in common. See Figure 1.7a and 1.7b. The elements common to P and Q form the intersection of P and Q, which is written P intersect Q. This set, P intersect Q, is the set of all elements in both P and Q. For the Venn diagram, we assume that the sets P and Q may have elements in common. See Figure 1.7a and 1.7b. The elements that are in P, in Q, or in both form the union of P and Q, which is written P union Q. This set, P union Q, is the set of elements in P or Q.